In this video, we are going to see how to determine if a directed graph has a cycle and output a cycle if it does. The algorithm will be a simple modification of an algorithm we have already seen, that is depth first search. 2 lectures ago, we went over depth first search, but we just looked at examples in undirected graphs. So now let's look at an example in a directed graph. The code is exactly the same, although now we only consider outgoing edges from the vertex we are currently visiting. Let's consider this example graph on 6 vertices. The order in which we visit vertices in the depth first search depends on the order of out-adjacent neighbors given in the adjacency lists. So I've explicitly given the adjacency list we will use for this example. Now let's remember the basic version of depth first search. In order to explore all of the vertices of the graph, we are going to have an outer function, which I'm going to call DFS now. We have an array of booleans called marked, which is initialized to be all false. In DFS, we cycle through all the vertices of the graph, and for any vertex which is not yet marked, it explores that vertex by calling another function, DFS visit. So DFS visit is actually the key function where all of the main work is going to happen. So let's look at DFS visit now. Here's the function DFS visit. When we first visit a vertex, we mark it. As we have a directed graph, in the for loop, we only iterate over the vertices out adjacent to V. So we look for an out adjacent vertex that is not marked, and when we find one, we recursively call DFS visit on it. When talking about depth first search in undirected graphs, we saw that DFS visit on vertex V marked exactly those vertices in the connected component of V. The situation is a bit different in directed graphs, so we need a new definition. Say that a vertex U is reachable from a vertex V if and only if there is a directed path from V to U. Because in the for loop, we only consider vertices that are out adjacent to the vertex we are currently visiting, DFS visit will only explore vertices that are reachable from the vertex V that we start at. In fact, you can show that DFS visit on V will mark exactly those vertices that are reachable from V. Now, the reason why this is true is very similar to the argument that we gave in the undirected case, so I'm not going to go through the details here. Now let's see how to modify DFS visit so that if there is a cycle that is reachable from the starting vertex V, then we can find it. Then the outer loop function, DFS, can call this modified version of DFS visit to find a cycle in a directed graph if it has one. So as an example, we're going to look at calling DFS visit on vertex 4 in our example graph here in the top left. So note that this graph does have a cycle on vertices 1, 2, and 3, and that this cycle is reachable from vertex 4. So we want to see how we can find this cycle. The key to do this is to keep track of when we call DFS visit on a vertex and when this call finishes. So to keep track of this, we're going to use another array called onStack. This is initialized to be everywhere false. In order to output the edges in the cycle if we find one, we also have a vector called edge2. This vector is initialized to be -1 everywhere. We use -1 because it's not the valid name of a vertex. Edge2 of U will hold the name of the vertex from which we visited U in calling DFS visit. Let's go over the changes to the code now. So when we start DFS visit on a vertex V, we set the corresponding entry of onStack to be true. And when the call to DFS visit on vertex V terminates, then we set the entry to be false. The other change is that before we call DFS visit on vertex U, we record the name of the vertex from which we visit U. So when we are visiting U from vertex V, we set edge2 of U to be equal to V. So the claim is that if during depth first search, we find a neighbor of a vertex that is on stack, so for which on stack is true, then we have found a cycle. So there's just a small addition here that we need to make to the code. We add an additional conditional to check if U, this vertex out adjacent to the V that we're currently processing, is on the stack. And if so, then we have found a cycle. And just note that if the vertex is on the stack, then of course it has already been marked. Okay, so it won't satisfy the condition of the first if statement. So you can see this code working at the given Godbolt link. So this kind of edge, an edge from the vertex we are exploring to a vertex that's already on the stack, is called a back edge. If we find a cycle, we can also explicitly output what it is. So let's start at U, this vertex which is on the stack, and such that there's an edge from V to U. So we know there's an edge from V to U. Then there's also an edge from edge to a V to V by the definition of edge to. And we can keep going backwards like this using the edge to relation until we hit U again. And we know that we'll eventually hit U again because U is on the stack. So I'll talk about why this is true more later, but first let's look at an example. So let's see what happens when we run DFS visit starting on vertex 4. So again, note that there is a cycle in this graph between vertices 1, 2, and 3 that's reachable from vertex 4. Okay, so we call DFS visit on vertex 4. So vertex 4 becomes marked, and we set the corresponding entry of on stack to be true. I'm going to represent the on stack array like this with green and red colors. So when a vertex goes on stack, I'll put the vertex number in green, and when it goes off stack, I'll put the vertex number in red. The first entry in the adjacency list of 4 is vertex 5, and vertex 5 is not marked, so we're going to visit vertex 5 from vertex 4, and we indicate this in the edge to relationship. So I've indicated that with this red arrow here. That indicates that we visited vertex 5 from vertex 4. So now we call DFS visit on vertex 5. So we mark vertex 5, and it goes on stack. I color vertex 5 green now to indicate that we are actively in the call of DFS visit on vertex 5. Vertex 4 is colored blue to indicate that the call to DFS visit on vertex 4 has not yet terminated. So vertex 4 is still on stack. Now vertex 5 has no out adjacent vertices, so there's nothing to do in the for loop in DFS visit on vertex 5. So vertex 5 goes back off the stack, and the call to DFS visit with vertex 5 terminates. So I indicate this with the red 5 there. So vertex 5 has gone off the stack. And we color vertex 5 red to indicate that the call to DFS visit on vertex 5 has terminated. Okay, so now we return to the call of DFS visit on vertex 4. So I indicate that by putting vertex 4 green again, and we continue in the for loop with vertex 4. The next vertex to consider in the adjacency list of vertex 4 is vertex 2, and vertex 2 is unmarked. So we set the edge to relationship and call DFS visit on vertex 2. So we mark vertex 2 and it goes on stack. We only have one vertex to consider in the adjacency list of vertex 2, which is vertex 3. This is again unmarked. So now we set the edge to relationship and call DFS visit on vertex 3. So we mark vertex 3 goes on stack. And we again just have one vertex to consider in the adjacency list, which is vertex 1. This is unmarked. So we set the edge to relationship and call DFS visit on vertex 1. So now we're in the call to DFS visit on vertex 1. So we mark vertex 1 and we put it on stack. And now this is actually the key moment that we've been working waiting for. There's only one vertex to consider in the adjacency list of vertex 1, which is vertex 2. But vertex 2 is already marked, so the if statement is not satisfied, and we're not going to go visit vertex 2. But vertex 2 is still on stack, right? You see we have a green 2 in the on stack, and it hasn't been closed with a red 2. And you can also tell from the picture that vertex 2 in the graph is colored in blue. So we found a back edge. This is the key signal for the presence of a directed cycle. So now in the code, we would enter the if statement, and we could process this cycle on vertices 1, 2, and 3. Okay, so now that we've seen an example, let's see why it is that back edges determine the presence of directed cycles. So before we get to that, let me show you another interesting property of depth first search. So here I've gone ahead and finished DFS visit on vertex 4. Nothing much more interesting happened, as there are no more unmarked vertices to find, so just all the recursive calls unwound and DFS visit on vertex 4 terminated. But now look at the green and red numbers indicating when the call to DFS visit on a vertex starts and ends. This sequence has a very interesting property, which we might say that it's well parenthesized. So if we put an opening parenthesis at each green number and a closing parenthesis at each red number, then the parentheses are properly nested. So this kind of property is going to play a key role why back edges imply the existence of cycles. Okay, so now we've seen the algorithm, we've seen how it works on an example. The key to why the algorithm works is this claim that I mentioned before. There's a cycle reachable from vertex V if and only if in DFS visit on V, we find an edge to a vertex which is on stack. In other words, we find a back edge. So this claim says that the presence or absence of a back edge characterizes the graph having or not having a cycle. So this is nice because it transforms our problem from detecting a cycle to detecting a back edge. And we've now seen how we can modify the basic version of depth first search to detect a back edge. So what remains to do is to see why this claim is true. So for this kind of if and only if characterization, we have to show two things. The first is that if we find a back edge, then there is a cycle. And the second is that if there is a cycle, then there is a back edge. Okay, so I'm going to show these two things separately. Let's first see that if there is a back edge, then there will be a cycle. This is actually the easier direction to show. So let's say there's a back edge. So while exploring some vertex U1, we find an edge to a vertex U2, which is still on the stack. That is, the call to DFS visit on U2 has not yet terminated. But since we arrived at U1 during the call to DFS visit of U2, this means that U1 is reachable from U2. We know that we only follow outgoing edges in DFS visit of U2, so we will only arrive at vertices reachable from U2. So since U1 is reachable from U2, there is some directed path from U2 to U1. In fact, we can even find this path as it will be given by the edge-to relation. So this path from U2 to U1 plus the back edge from U1 to U2 gives a cycle. And this shows the first part of the claim. Before we get into the other direction, that a cycle implies the existence of a back edge, let's go over a general property of depth first search that is quite useful. We call this the unmarked path property. The unmarked path property says that if there is a path of unmarked vertices from U1 to UK, when DFS visit on U1 begins, then the start and finish time of DFS visit on UK will be nested inside that of DFS visit on U1. In particular, DFS visit of UK will finish before DFS visit on U1 does. The key to the unmarked path property is to show that DFS visit on UK starts before DFS visit on U1 ends. If DFS visit on UK is called while the call to DFS visit of U1 is still open, then DFS visit on UK will have to finish before the recursion can return to the call of DFS visit on U1 so that this call to DFS visit on U1 can eventually terminate. So what we need to show is that DFS visit on UK will start before DFS visit on U1 finishes. We can do this by showing by induction that DFS visit will start on all of U2, U3, etc. up to UK before DFS visit of U1 finishes. For example, this will be true for the vertex U2 because of the existence of this edge from U1 to U2. We will consider this edge from U1 to U2 in the call to DFS visit of U1. And when we consider this edge, either one of two things will happen. Either at that point U2 is already marked, in which case DFS visit of U2 already started and already finished. So in that case, what we want to show is true. The second case is that U2 is still unmarked when we consider this edge from U1 to U2. In that case, then we'll start DFS visit on U2 at that moment. Either way, DFS visit of U2 starts while DFS visit of U1 is still open. I want to highlight the importance of the assumption that the path is unmarked in this unmarked path property. So let's consider this graph here on 3 vertices. Suppose that we start DFS visit on vertex U0, and that from here we first visit vertex U1. So we take this edge to vertex U1. So now we're going to start DFS visit on U1, and at this moment, well, there is a path to vertex U2 from U1, but there is not an unmarked path because U0 is on this path and it's already marked. And you see that in this case, DFS visit of U1 will just finish straight away because its only out adjacent neighbor, U0, is already marked. So the conclusion of the unmarked path property is actually not true in this case. Here, DFS visit of U1 will finish before DFS visit of U2 begins. So it's really critical that we have this property that the path is unmarked. Okay, with that digression out of the way, now let's see the other direction of the claim. We want to see that if the graph has a cycle which is reachable from vertex V, then DFS visit on V will find a back edge. So for this direction, we suppose that the graph has a cycle. So here I've drawn a cycle. Let's say it's a cycle of length k. And we also assume that this cycle is reachable from our starting vertex V. So here's our starting vertex V. And since the cycle is reachable from V, we know that DFS visit on V will find a path to this cycle. So here I've illustrated the path that DFS visit on V takes to the cycle. Of course, it may follow some diversions off of this path. I've just illustrated the path itself. We suppose that U1 is the first vertex on the cycle reached in the call to DFS visit on vertex V. We can just rename the vertices appropriately so that this is the case. So now we reach U1 and we call DFS visit on U1. And now we can use the unmarked path property. When DFS visit on U1 starts, all of the vertices U2 through UK are unmarked. That's because of our assumption that U1 is the first vertex on the cycle that we reach in DFS visit of V. So the unmarked path property implies that DFS visit of UK will start before DFS visit of U1 finishes. And this is exactly what we need to see that we're going to find a back edge. So in DFS visit of UK, we will consider this edge from UK to U1. And since DFS visit of U1 has not finished yet, U1 will still be on the stack. So the edge from UK to U1 will be a back edge. So this finishes the proof that we find a back edge if and only if the graph has a directed cycle.